Hello. In this video, we're going to talk through some periodic trends AP release questions. Some of them are multiple choice, some of them are free response. So this first one, we want to know what property generally decreases across the periodic table from sodium to chlorine. You will notice that they are all in sodium and chlorine, they're all in row 3. That means that the third shell is the valence shell, but the difference is the effective nuclear charge is going to increase as you go across that row. So as a result, the first ionization energy and electronegativity increase, but we want to know what decreases. Well, what decreases then is the atomic radius. Because over here, chlorine is going to have a higher effective charge, so it's going to have a stronger attraction for that valence shell. So it's going to pull those in closer, making your atomic radius smaller. All right, next one, we're looking at sodium versus neon. And sodium versus neon, we're comparing about their effective nuclear charges. Let's just quickly calculate what those are. So the effective nuclear charge, remember, is the number of protons minus the number of core electrons. So sodium's got 11 protons, 10 cores, so it's got an effective charge of +1. Neon has 10 protons and 2 core electrons, so it's got an effective charge of +8. So neon's got a much greater effective nuclear charge. So we want to know which of these statements would be kind of explained by this difference in effective charge. So density, not really relevant. First ionization energy, sodium has a lower first ionization energy than neon. Yep, that matches what we're seeing here with effective charge. So sodium's got a weaker attraction for its electrons than neon. So that sounds like a good answer, but let's go through the other ones just to check. So C, melting point, does not seem to be relevant. Neutrons to protons, that's not relevant to what we're talking about here. And isotopes, that's also not relevant. So effective nuclear charge will affect properties like atomic radius and ionization energy and electronegativity. Next one, we're looking at some successive ionization energies. So what we want to notice is the ionization energies always increase as you remove more and more electrons from an atom, but we'll see that there's a big jump between the third and the fourth ionization energy, and that tells us that these first 3 electrons were on the valence shell, and then this fourth electron, since it's so much harder to remove, this must have been from an inner shell. This must be a core electron. And so what that tells us then is it looks like this atom has 3 valence electrons. And the reason why I know that is because, just to clarify here, the fourth electron is much harder to remove than the third one. So I can infer that that fourth electron must be a lot closer to the nucleus. So then you look at which element has 3 valence electrons. Of these options, only one of them has 3 valence electrons. So it must be aluminum. And let's look at fluorine versus oxygen. What helps to account that the fluorine ion is much smaller than the oxygen ion? Let's take a look at those. So fluorine -1, fluorine has 9 protons, and it would normally have 9 electrons, but it gained 1, so now it's got 10 electrons. Oxygen has 8 protons, and it also has 10 electrons. So these two species are what we call isoelectronic. I'll just throw that word out there for you. That means they've got the same electron configuration. So, but the F- ion is smaller than O2-. And looking at this information here, I can already see it's probably because fluorine has more protons. So it's got more protons attracting in those electrons. So mass has nothing to do with it. Fluorine has more electrons. C is just not a true statement. Polarizable, you might be like, what are they talking about there? It seems like the thing that really explains why fluorine has a smaller radius is because it has a larger nuclear charge. There's more protons in the nucleus that are attracting in those 10 electrons. So therefore, this is going to have a smaller radius. Which of the following explains why the electron affinity of Br is greater than iodine? So electron affinity, remember, this is the one that's kind of opposite of the ionization energy. Electron affinity is the energy to add an electron. So if bromine has a greater electron affinity, greater magnitude, than iodine, that means that bromine seems to have a greater attraction for electrons than iodine. So if we think about bromine and iodine, they're in the same column on the periodic table. So that means they're going to have the same effective nuclear charge. What's different is those valence shells are in different shells. So let's see, which of these makes the most sense? So it seems like there's greater attraction between electron nucleus and bromine than iodine. This D seems to match what we're saying here. Going through these other ones, let's kind of make sure these other answer choices are wrong. So bromine has a lower electronegativity than iodine. That's not true there. It actually has a higher electronegativity. It also has a higher ionization energy. So A and B are just false statements. C is also a false statement. So they're both end in like P5. So they both would just be adding an electron to a P subshell. So C is also not true. So D is the only one that's actually a true statement. And it also fits with what we're observing here. Okay, 7. Which of the following electron configurations corresponds to where there's an especially large jump between the second and third ionization energies? So we are looking for an electron configuration where you would have 2 valence electrons, basically. That's what this is saying. That would give us a large jump in energy between the second and third ionization energies. Number 7 is really similar up here to this question right here, number 4. So remember how we said the difference, let's see, the step that gives us like the big jump, big difference in ionization energy, that tells you how many valence versus core electrons there are. So this is basically saying which configuration would match with having 2 valence electrons. So N represents the shell number. So let's just throw a number out there. Let's pretend, let's throw the number 3, just in case it helps clarify it. So 3s2 versus like 3s2, 3p1, 3s2, 3p2, or 3s2, 3p3. Basically, we're wondering which of these has 2 valence electrons. And so it looks like the answer right here is A. This one has 2 valence. This one would have 3 valence. This would have 4 valence. This would have 5 valence. So only this first one matches with having 2 valence electrons. And let's draw this out again real quick. So what that would look like is, let's say you've got 2 valence electrons. You remove the first one, you remove the second one. That takes some energy. But then if you want to remove a third electron, it's now coming from the second shell. So now this electron is a lot closer to the nucleus. It's much more attracted. It's harder to remove. So that's what we're going to see here in the data. We're going to see that the third ionization energy is going to be a lot greater than the first and second. So that tells us that there are 2 valence electrons in this atom. So those first 2 electrons are much easier to remove than the third one. All right. Which of the following explains why electronegativity of chlorine is less than fluorine? So you want to look on your periodic table. Chlorine and fluorine are in the same row. Fluorine has, let's see. So sorry, I said row, I meant column. They're in the same column. So they both have similar effective nuclear charges. They both have effective charges of +7. But fluorine's valence electrons are in shell 2. Chlorine's are in shell 3. So the electronegativity is due to that difference in the shell location. So if we go through our answer choices, it has nothing to do with mass. Okay. The chlorine nucleus contains more protons than the fluorine nucleus. Well, that is a true statement, but it doesn't really seem relevant to what's happening here because their effective nuclear charges are actually the same. So that doesn't really seem to explain here. All right. When the chlorine, this is a long one. Okay. the fluorine are shielded from the positive fluorine. Because chlorine is larger than fluorine, this one is sorry, I haven't read through these last 2 answer choices yet. What to do? The chlorine bonding electrons are more shielded from the positive chlorine nucleus than the fluorine bonding electrons are shielded from the positive fluorine nucleus. This is like very wordy here. Yeah, it looks like the correct answer choice is C, but this is a very wordy choice here. If you look at why D looks wrong, is it says the repulsions among electrons in the valence shell of chlorine are less than repulsions among electrons in the valence shell of fluorine. That one seems like an incorrect statement because their valence shells look nearly identical. They both are, you know, S2P5. So their valence shells are going to have this, both have 7 electrons. So that's not really the significant difference here. What it has to do with is the fact that chlorine's electrons are further from the nucleus, which is what kind of C seems to be getting at. They're more shielded. Shielding is going to come with the distance. So as you're further from the nucleus, you've got, you know, more core electrons between you and the nucleus, and you've got more shielding there. So yeah, it looks like C is our correct answer there. All right, so that's our multiple choice ones, and we'll have a different video going over the free response.